Hi, I'm picking up with our worksheets on page 6 about dilutions. So we had used the dilution equation, m1v1 equals m2v2, to calculate the concentration of a diluted solution, or in this case, in our next example, we're looking at the volume that we would need of a concentrated solution to make a more dilute solution. For example, if you're setting up a lab for students, you might take an amount of the concentrated stock solution and dilute it to a larger amount for students to use in their experiments. So we'll identify those variables and plug into the equation. So what volume of, there's our multiply, 6 molar hydrochloric acid is, that's our equals sign, required to prepare 50 milliliters of a 0.150 molar solution. So we have 3 of those things, right? We've got a molarity, another molarity, and a volume. And so we're essentially looking for what is that, what's that second volume? Yeah, so you could, the labels, you can label either one, V1, V2, but we've got 3 out of the 4, so you can either plug it in directly, like the way I used to do this. I think it's not as standard now. I might say, how many milliliters do I need, right? I know it's going to get multiplied. How many milliliters do I need of that 6.00 molar solution? Shoot. Let me start that over. How many milliliters do I need of that 6 molar solution in order to create that M2 that I'm looking for? Yeah, so I guess the 1 and 2 make sense in this case. So we're looking for 50.0 milliliters of 0.150 molar solution. All right, so you could think of just dividing both sides by that molarity. On both sides. And so we will get the V1 that we need. All right, 1.25 milliliters of that concentrated stock solution. That's the 6 molar solution. Yeah, so pretty small amount to make our 50 milliliters of more dilute hydrochloric acid. And the same thing will work, same equation will work in this case down here where we have the percent concentration, weight per volume. Because those units match, we don't even need to worry about converting those volumes. They'll just cancel out like we saw here, right? Those molarities cancel out. So in this case, we're looking at C1V1 equals C2V2, where C stands for whatever the concentration units. And we also have that explain how. So we're going to come back at the end and put it into words. Okay, let me scroll this up a little bit. So we need to find the V1 again, how much stock solution to make 1,000 milliliters. So let's go ahead and leave that in milliliters. Of that 0.90% NaCl solution. And we're starting with that more concentrated solution, which is 5.00% NaCl solution. Okay, I'll need 180.0 milliliters. And this is another case where even though we only have two significant figures in the percentage, we want to measure it more accurately because we can. So we'll go ahead and measure 180 milliliters of the concentrated NaCl solution. Right, that's that 5%. And then we need to figure out what is the other amount. Right, so we're looking for the total as 1,000. So we'll have to subtract that. So as we explain, we will say measure 180 milliliters of 5.00% NaCl solution and add 820 milliliters of water. Mix thoroughly. All right. So not so bad. Just use words. Explain just means words. What we would not do is add 180 milliliters to 1,000 milliliters because then we'd have too much volume. So that's the usual tricky part in dilution questions. All right, I want to talk a little bit about ion concentrations. We might have an ion concentration that is greater than the solution concentration. Right? Concentration of ions may be greater than the concentration of the compound. And that happens in the case of something like ammonium phosphate. So take a minute and write that formula. What is the neutral formula for ammonium phosphate? We have the ammonium as NH4, 1 plus, and we have a phosphate, PO4, 3 minus. So we're going to need multiples of those ammonium ions. So that is NH4. And because each one brings in a positive 1, we're going to need 3 of those to counterbalance that phosphate, which is PO4. Right, so that's the neutral compound. If we have 1.00, and I'm going to pop that out into its conversion factor, the number unit and label on the top and the bottom. So this is 1.00 moles of ammonium phosphate. So that is NH4 3PO4. I know it's not super clear. Oh, it's not so bad. Over 1 mole, 1 liter total solution. So how many moles of NH4 plus? Oh, and this is where I'll go ahead and format this out. How many moles of ammonium are in. Oh no, it's not even asking for moles. Well, it's asking for molarity. So let me add that moles. We'll make this a molarity by putting liters of solution in the denominator. So now I'm building that molarity of just the ammonium ion, and we are going to start with this factor here. So I'll just bring it over. If we start with 1 mole per liter of ammonium phosphate solution, we're going to use that mole-mole relationship to change the label. So we want to cancel out the compound. So 1 mole of NH4, 3PO4, ammonium phosphate. For every 1 mole of ammonium phosphate, we want to figure out how many moles of NH4, here we go, plus 1. I'll just do plus, there we go. Is that clear? Well, you can see from the compound, there are 3 ammonium ions for every 1 formula unit of ammonium phosphate. So that means in this solution, we will have 3 molar, or 3, sorry, let me keep my sig figs, molar NH4+. All right, keep that looking nice and normal. So it has a higher concentration of ammonium than it does of the original solution because each formula unit will dissociate completely into those 3 ammonium ions because it's soluble. What about phosphate? What is the molarity of the phosphate? What molarity of PO4? 3 minus. In that same solution. Well, those are going to have 1 phosphate for 1 compound. So that's going to be equal to the 1.00 molar solution. PO4, 3 minus. Right, because they're 1 to 1. So we can apply that thinking to these other compounds as well, and that's why, in part, it's so important to know how to write your factors, write your mole-mole relationships. I'm sorry, because it's so important to write your names, the neutral compounds, that's what I meant. Okay, calcium hydroxide. Hydroxide has a 1 minus, so there's going to be 2 hydroxides. And then same thing with lithium sulfate. You'll need to write that formula. Okay, so if we have 0.5 molar calcium hydroxide, that's 1 to 1 with calcium. This is going to be 0.500 molar. And then the hydroxide is double that. 1.000. You could think of it as adding or whichever. We're not too worried about the sig figs here. So the square brackets indicate molarity. That implies that your units are going to be molarity. Lithium sulfate, similar kind of a question. In this case, we're looking at lithium with SO4, which has a 2 minus. So SO4. So that's going to be 2 lithium for every 1 sulfate. That'll give us 3.00 molar lithium ion and 1.50 molar sulfate ion. Okay, those become useful in the future. I don't think we're going to do too much with them this quarter. We have just 1 more week of class. So you may see those in the future. All right, so jumping back into chapter 9, stoichiometry. So when we interpret that chemical equation, we're looking at the number-particle ratio. So we can think of these as molecules. We're breaking up those original molecules, forming a completely new product, the ammonia, and the coefficients give us the number of each kind of molecule. Those have to be whole numbers. But when we're looking at a huge collection of molecules, for example, it could be 1,000, in which case we would have 2,000 hydrogen to 1,000 oxygen to 2,000 water. Or it could be Avogadro's number, right? So this could be 2n, n, and 2n. You see, I'm just using those coefficients to keep track of the ratio. So if we're talking about Avogadro's number, then we can just use moles. That gives us a word for it, the moles. So basically saying, okay, there's 2 moles of hydrogen for every 1 mole of oxygen, and that will produce 2 moles of water if they react completely. So those coefficients give us the mole-mole relationships. All right, let's fill in a couple of these. Here's an equation. This is ethene, or ethylene, burning in oxygen, combustion, producing CO2 and water. And so I can just say, okay, for every 1 mole of ethylene that burns, it's going to require 3 moles of oxygen, and that in turn will produce 2 moles of CO2 and 2 moles of water. We can construct a mole-mole relationship, a conversion factor, for any 2 things in the compound. So I like to think about it actually a little bit like this. If we make columns for each of these things between each of the reactants and products, anytime you want to cross through the equation, cross one of those lines, you are going to need to be in moles. You're going to need to change the label. Right, so here's the label. From one chemical to another. And we can do that by writing the mole-mole relationship and just filling in the values. So for every 1 mole of ethylene consumed, we will produce 2 moles of CO2. Now coincidentally, well, never mind. Let me not get distracted. Okay, we're using the coefficients again. So for every 3 moles of oxygen consumed, we will produce 2 moles of CO2. For every 1 mole of ethylene consumed, we will consume 3 moles of oxygen. Or for every 1 mole of the fuel type that's burned, the ethylene, will produce 2 moles of water. So we could go between any 2 things that we need to, just change the label based on those coefficients. Mathematically, it looks similar to what we've done before, but now we're going to use the mole-to-mole relationships from a chemical equation to change those labels. So let's do a few of these. How many moles of oxygen are needed, here's the equal sign, to completely react with 2.5 moles of propane? Okay, so how many moles of O2 are needed to react with 2.50 moles of C3H8. Common fuel, you can see it in those big tanks like at the gas station to fill like your barbecue grill. Those point sources are a big source of leaks of greenhouse gases as well. Okay, C3H8, right? Just canceling that out, I want to go to moles of oxygen, so I'm going to introduce moles of O2 on top, and then I'm going to find those coefficients and use those coefficients. So let's see, here's the oxygen, and here's the propane. So that gives us the directions of what to do. It's going to take 5 moles of oxygen to burn 1 mole of propane. 12.5 moles of oxygen. How many moles CO2 will be formed when you use up 3.50 moles of O2? Same process. Cancel out moles of O2 because they don't show up on the answer side. We're going to introduce moles of CO2. And using that chemical equation, we see that we will produce 3 moles of carbon dioxide for every 5 moles of oxygen consumed. And don't forget your significant figures, keep that 0. 2 moles of CO2 would be produced. And one more. Steam is water vapor, and that's what's formed here. So how many moles of H2O will form when at the same time that 4.50 moles of CO2 will be formed? Again, we're referring back to that chemical equation up at the top, canceling out moles of carbon dioxide and going to moles of water. And that is 4 on top and 3 on the bottom. And again, I do those as separate steps just to give time for that ballpark check, just to double check, make sure you've got it right. So 4.5 times 4 divided by 3, and I get 6.00 moles of water, or steam, formed. Oh, I got an extra space in there. Okay. Oh, I got one more. All right. How many moles of propane will react to produce 2.5 moles of CO2? Oh, there we go. I'll keep those all up there. All right, canceling out moles of CO2 and going to moles of propane, C3H8. And now I'm going to scroll up to take a look. And that was 1 propane for 3 CO2. So 1 mole of propane will produce 3 moles of CO2. Or 0.83333 repeating moles of propane. I think I may have just said that incorrectly a minute ago. Okay, there we go. Now that's going to look a lot, computation-wise, that's going to look a lot like the calculations we did in chapter 8. In those calculations, right, we were just now working on the moles of one thing to moles of another, and we did that before where we used the mass. But now we're going to sandwich the mass on either side and use the mole-mole relationship that comes not from the formula but from the chemical equation. So those are both valid ways to make that conversion. So let's take a look at what we've got. Calculate the mass of CO2 needed to react completely with 50 grams of Fe2O3. So I like to notate these a little bit. We're going to start with 50 grams of this one, and we're looking for mass of CO. How many grams of CO? So let's go ahead and write that out. How many grams of carbon monoxide will be consumed when we start with 50.0 grams of Fe2O3? So our first step, we're going to change the mass of the Fe2O3 into moles. So we'll cancel out grams Fe2O3 and go to 1 mole. And for this, we're going to need a little side calculation. Right? 2 times 55 plus 3 times 16. 159.7 grams. Okay. And then grams are out of there. And now we're in moles. So we're at this section, moles of what we were given. Now we're going to change the label using a mole-mole relationship. So we'll cancel out moles of Fe2O3, and we're going to use a mole-mole relationship to introduce moles of CO, because that's what's over on the left side. Looking at those coefficients, I've got a 3 in front of the CO, and I've got a 1 in front of the Fe2O3. Now that is iron 3 oxide, of course. I'm just naming the formula so that I don't type the wrong thing. It's hard to type one thing and say a different thing. Okay, now let's see, we're looking for grams on top. We've got moles down here, so 1 mole of CO. We want to go to grams of CO, and so that is 28.01 grams of CO. And let's go ahead and cancel the rest of those. Moles of CO are out, and we're left with grams equals grams. So we can just do this in order. 50 divided by 159.7 times 3 times that answer in my calculator, 28, and I get 26.308 grams of carbon monoxide. Now let's take a look at our significant figures. We started with 3, so we'll end with 3. Okay, let's get some practice doing that. Okay, on your paper, you will need to refer back to the equation. So go ahead and get a start, get ahead of me if you can. We want to know how many grams of iron will be produced at the same time that we produce that we react 125 grams of carbon monoxide. So you can use that little solution map going grams to moles, moles to moles, moles to grams, or you can think of it in terms of dimensional analysis where we just need to get rid of those grams. What do you have? Well, when in doubt, just go to moles. And that was, we had that already, it's 28.01. So sometimes what I'll do is make a little table with my problem where I list out the molar masses of the compounds I'm going to need. Okay, grams are out of there. I need to cancel out moles of carbon monoxide and go to moles of iron. Now this is going to come from the chemical equation, so let me go get those coefficients. All right, be careful because I have carbon monoxide and carbon dioxide. That can be a little confusing, a little error prone there. But anyway, 2 iron for 3 CO. Two iron for 3 CO. Great. All right, moles of carbon monoxide are out of there. I'm in moles of iron. We need to cancel out moles of iron, and we're going to use that molar mass right off the table. Grams of iron, 55.85 grams of iron in 1 mole. And now we're ready to calculate. So if, unless we made a mistake with our numbers, we should get the right answer. So 125 divided by 28.01 times 2 divided by 3 times 55.85. You can string it all together, and that helps keep track of where you are in the calculation so you don't have to use parentheses or write down intermediate values. And then let me identify my significant figures. Just 3 given in the problem, 166 grams of iron. Great, how's it going? Why don't you go ahead and start the next one on your own while I format it out here. If you need a little more time to get ahead, feel free to stop the video and then let it play while you're finishing it up. Oh, I haven't looked at the CO2. Let me go take a look at the CO2, 3 of those as well. Okay, in the calculator we've got 75 divided by 55.85 times 3 divided by 2 times 44.01, and we get 88.65 grams of CO2. And that will be good to 3 significant digits, but I'd only round that if you're presenting it at a paper, you know, or a poster presentation or something like that. Okay, let's see, shall we go a little further? Maybe I will just get started on this next section. If I've made any mistakes or if you have any questions, please let me know. Yeah, we'll go ahead and get started with the stoichiometry. Limiting reactant. So we're going to introduce these terms, the limiting reactant, the theoretical yield, and the percent yield. So these work a lot like a recipe, just like cooking, where you would compare what's in the recipe to what is on the shelves in the cabinet. So the recipe is like the chemical equation, and then what you have on the shelf is like what you put together in the flask to make the reaction go. So typically there's going to be some stuff that you have extra, right? It's rare that you would make some cookies and run out of exactly the flour and the sugar at the same time. So let's take a look. Oh my God, Cat. Oh, sorry, he just jumped on me with claws. Okay. All right, we'll keep going. So if we were going to sell a bicycle, we need the whole thing. You're not going to sell a bicycle with one wheel, for example. So it's like our recipe for the bicycle is one frame, one seat, two pedals, and two wheels. And there's some other parts, but let's just work with that. So our basic structure of the question is always going to look like this. Well, when we're figuring out which one's limiting, we're going to ask how many of the final things could we make with the things we have in the shop. We've got 5 frames. Okay, so with 5 frames, you could make 5 bikes, right? That one's really easy because they're 1-to-1. 6 seats. Well, you could make 6 bikes with 6 seats, but you'd run out of frames, so you can't make 6 bikes. You can only make 5 bikes, and then you'd have 1 extra seat, right? So we're going to use those exact same principles for our problem solving in chemistry. It seems pretty intuitive with the bicycle, and especially with frames and seats. But as we move forward with chemicals, it can get kind of confusing. So we're going to set up the structure the same way, where I'm going to say, okay, how many bikes could I make if I started with 15 pedals? And we know from the picture, or maybe from your experience riding bicycles, that one bike has 2 pedals. So theoretically, we could make 7.5 bikes, right? But we're never going to make a half a bike. In this case, we're going to have to round that down. So really, we could make 7 bikes. And then we would have used 14 pedals. Oh, geez, how come I can't get that? There we go. You would have used 14 pedals and have 1 pedal left over. All right. Oh, but we can't make 7 bikes, right? Because we're going to have to just make 5 bikes. What about 8 wheels? Let's take a look at that one. So our process is that we're going to look at how much product we can make starting with each ingredient that's listed. So if we have 8 wheels, and we know that there are 2 wheels per bike, then you can see, and you may have seen this way faster than I can type it, that this would allow us to make 4 bikes. And it would use up all the wheels. And that is the smaller amount, right? So this is going to be the amount we produce. This is our theoretical yield. Is 4 bikes. All right, and I don't like the red. That's too much. There we go. What does that mean? That means that if we want to assemble the bike and everything goes according to plan, right? We don't wreck anything. We don't damage any parts in the process. If everything goes just right with with 5 frames, 6 seats, 15 pedals, and 8 wheels, we could make 4 bikes. That is the theoretical yield. And that means that our limiting reactant is what? Is what we started with, 8 wheels. So the limiting reactant was wheels. And then when we have excess, that would be everything else, right? Now, if we want to find out how much, we will have to do a subtraction step. So when we made 4 bikes, we used 4 frames. That means we're going to have 1 frame left over. 5 minus 4 frames left over. Now I'm doing these pretty quick because the numbers are easy, but normally you'll have to write out a long dimensional analysis step for each one of these. And I'm hoping to show you the table method by the end of this week, although I'm not sure we'll get to it. Okay, so one frame. Let's see, if we make 4 bikes and we start with 6 seats, then 6 minus 4, because we use 4 seats, that's going to be 2 seats left. How many petals are left? So let me do a little side calculation on the petals. We had 15 petals originally. And we made 4 bikes, so we used up 8 petals. Used up. Right? Okay, yeah. So that means we have 7 petals left over. Okay. 7 petals left. Anything else? No, that's it. That's it. We used up all the wheels. All right, so that's an outline of this whole process, and now we're going to be using our mass to mass calculations, that whole mass to moles, moles to moles, moles to mass, to do each one of these. Every time you want to figure out how much got used up or how much you could produce, we're going to do that whole calculation. You could stop at moles because that fundamental relationship is about pieces, the particle ratio, just like here. So we'll take a look at a number of different ways to look at that. Okay, so in your textbook, they compare the 2 reactants. They say, okay, figure out how much of this and figure out how much of that and figure out which one's smaller, and then you still have to figure out how much is produced. So I'm going to suggest a different method overall. And that is to always look at what is the product. So I would say you're always going to look, what are we looking for here? Number of moles of H2 gas. Always look for a product. So we're asking, if we start with HCl, how much could we produce? If we start with aluminum, how much could we produce? And then from there, we're going to pick which one is smaller. Right, so the smaller amount. And then you've already finished the problem. Right, you've already figured out how many bikes you could make or how many cookies you could make. So rather than converting between 2 reactants, I suggest you look for a product. Okay. Then you'll just pick the smaller amount, and the one that you started with that led to that smaller amount is limiting, and the other thing is in excess. If you have 3 reactants, then usually one will be limiting and everything else will be in excess. If you want to set it up so that they all react exactly like 1 to 1 to 1, that you can do as well, and those are considered the molar equivalents. So you're going to, design your experiment so that you have exactly the right amount. So let's go ahead and do one of these. How many moles of H2 can we get if we start with 5.00 moles of aluminum? So that's one calculation. Oh, and let me go ahead and start the next one. I'm going to do 2 parallel calculations because we were given 2 reactants. So how many moles of H2 could we produce if we started with 5.00 moles of HCl and all of it was used up? So we're going to do these 2 parallel calculations using that mole-mole relationship from the chemical equation. So go ahead and write ahead of me if you can. Canceling out what we started with and converting to what we're looking for. I do suggest you do that in 2 steps with the units first and then the labels, and I'm just doing them all together because I'm typing and it takes a long time. Okay. So this is what? 15 divided by 2. This is 7.50 moles of H2 produced if and only if, the limiting reactant equals aluminum. So if all of the aluminum is used up, and I usually put some stars around here, so this is a big if and only if. All right, let's take a look at the other one. This is going to be 2.50 moles of H2 produced if the limiting reactant was HCl. All right, so we're going to pick the smaller amount. I like to mark this really clearly in my work. Right, so there it is. That means that, let's fill this in. Yeah. Okay. That means the limiting reactant is the HCl, and the amount excess will be aluminum. There are going to be little chunks of metal left over, and then indicate the number of moles hydrogen gas produced in this reaction. This is the theoretical yield. We already calculated that. We expect 7.50 moles of aluminum. And normally we're going to convert that to grams because most people are more comfortable with grams of aluminum. You wouldn't say, to your friend in the garage, hey, do you have a 2.5 moles of aluminum? Usually you might say, I need 5 grams for this, project I'm doing. Okay, so let's take a look at one more. Burning of propane. Good, I got the whole problem on the page. Here's our balanced reaction. And we want to calculate the number of moles of CO2 produced when you start with 1.5 moles of propane. So again, it's propane, that's the C3H8. I would just list it there because then it's easier to keep track. Right underneath the compound there. And that's going to react with 5 moles. Oh, so it's a 5 in front, but it's also 5 moles given of the oxygen. Okay, so we'll set up 2 parallel calculations. And we're going to look for, calculate the number of moles. So here's what we're looking for. How many moles of CO2? Okay, we'll identify what is limiting, what is in excess, and indicate the theoretical yield. Right, so find the theoretical yield. The theoretical yield is, and you will have already calculated it. Okay, we'll pick up there on Tuesday. See you then.